Okay, this lesson is going to be on a review of the index laws, also on graphs of exponential functions and differentiating exponential functions. So you can see at the top of the page here is a list of the index laws. Remember, when you're multiplying indices with the same base, remember the A is the base and the M and the N's are called the either the powers, the exponents, or the indices. When you're multiplying indices with the same base, you add the powers. When you're dividing indices with the same base, you subtract the powers, and notice that the base stays the same. When you've got a power of a power, you multiply those powers and the base stays the same. Anything to the power of 0 equals 1. You've got the negative index law, so anything with a negative power becomes a positive power on the denominator of a fraction. If you've got two things in brackets raised to a power, both of those things have been raised to that power. Likewise, if you've got a fraction in brackets raised to a power, both the numerator is raised to that power and the denominator is raised to that power. And then we have Ned and his donkey, where N stands for the numerator, D stands for the denominator, or Ned and his donkey, numerator, denominator. And Ned gets to sleep inside the cave and the donkey's outside. So on the worksheet that I gave you in class here, there's a couple of examples. So the first question there, keeping the base the same and adding the powers. Keeping the base the same and multiplying the powers there. And keeping the base the same and subtracting the powers. If you've got multiple things in the brackets, you've got to raise everything into the power of 4 in this example. So you've got 3 to the power of 4, which is 81. You've got m squared to the power of 4, which means you multiply those powers. And you got n to the power, and you got 1 times 4, which is 4. Okay, anything to the power of 0 equals 1. In this question here, you've got 6 times 1, which is 6. And then you've got a couple of other questions here to do when you're dividing. So divide the coefficients and subtract the powers. 8 minus 4 is 4. You can probably do those other questions on your own. Let's looking at some other questions here where we've got to the negative index law. So remember, that becomes a positive power of 1 there on the denominator, but normally you would just write that as 1/5. Likewise, this would become 1 on 2/3. Okay, or that's equal to 1 on 8, because 2 to the power of 3 is 2 times 2 times 2, which is 8. Let's have a look at F here, a negative fractional power. So that's 1 over 9 to the power of a half, because the negative power becomes a positive power on the denominator. And then remember, fractional powers, 9 to the power of half is the same as the square root of 9, which is 3. So the answer is 1 on 3. This 16 to the power of negative a quarter is 1 on 16 to the power of positive a quarter. And 16 to the power of a quarter is 2. Because that's like the fourth root of 16. That should be a 1 there. That looks a bit funny. And then this one's H is a little bit hard to read, but that is saying 1,000 to the power of negative 2/3. So that's 1 over 1,000. Oh, it looks like zeros to the power of 2/3. And then using Ned and his donkey, that would mean 1 over 1,000. Ned is inside and the donkey is outside. So you can either do 1,000 to the power squared and then cube root that, or you can do the cube root of 1,000 first and then square your answer. So that's going to be 1 over 100. Okay, we've got a couple of other combination questions here, this time with numerical bases, but the index laws all still are exactly the same. So you're keeping the base the same here in A. The base is 5. And you add the powers. Alright, so you're adding the powers. 2x plus 3x is 5x. And then we have to divide that by 5 to the x. So keeping the base the same and now subtracting the powers. 5x minus 1x is 4x. Okay. The other questions are all going to be very similar in this question. When you've got the bases the same, really easy, add the powers. The bases are the same here as well. First using the powers of powers and then adding the powers. Question D though, we don't have all the same base. So the key to these questions is to change them so that they do have the same base. Then you can use the index laws. So we can change 8 to 2 cubed, and then 2 cubed all to the power of 2x become the 3, and the 2x, those powers would multiply, so they become 2 to the power of 6x. Oh, then we've got 2 divided by 2 to the power of 6x. And then times by 4 to the power of x. I guess we can leave that like that, because 2 to the power of x divided by 2 to the power of x is 1. Times 4 to the power of x is just going to be 4 to the power of x. We could, if we wanted, changed the 4 to 2 squared, which would become 2 to the power of 2x. But either answer would have been okay. Okay, in E, you want to change 9 to 3 squared. And then that's to the power of 3m plus 1, which means, so it'd be like this. You got a power raised to another power, which means you're going to be multiplying those powers together. So you would have, and then we've already got the base here of 3, so we don't have to change that because now our two indices will have the same base. So that's 3 to the power of 6m plus 2, because powers of powers means we multiply those powers together. And now we're multiplying powers, so keep the base the same and add the power. So we've got 6m plus 4m, so the like terms, and we've got 2 minus 1. So the answer is 3 to the power of 10m plus 1. Okay, and then in F, I'll leave that one for you to do yourself. I would suggest changing all of these numbers to base 2. So 4 would be 2 squared, 8 would be 2 cubed, and 32, that is going to be 2 to the power of 5. Okay, some other questions. So I'm solving some exponential equations. So to solve these equations, I guess in A, you're just going to do the same thing to both sides of the equation, which is finding the 7th root of both sides. So it's like that button on your calculator where you got to do the 7th root. Okay, so just put that in your calculator to see what the answer is. In B, first you got to do the square root of both sides. So you get 2 to the power of 5m equals the square root of 1,048,576, which is 1,024. And then remember, with solving exponential equations, you want to have the same base on both sides. So 2 to the power of what equals 1,024? Well, I think it might be, from trial and error, 2 to the power of 10. So we've got 2 to the power of 5m equals 2 to the power of 10. We'll continue this down here. Now that the bases are the same, both 2, then you can say the indices are equal. So you can say 5m equals 10, so m equals 2. So the trick, or the key with exponential equations, is to get the same base on both sides of the equation. Then you can say the powers or the indices or the exponents are the same. I'll just do one more question in this section. We'll do D, and we'll change 9 to 3 squared. And then remember, we've got a power of a power. So powers of powers means you multiply. So that becomes 3 to the power of 6a equals 3 to the power of 7. Then we've got bases are the same, which means exponents are the same. So just solving that linear equation there. So you'll be able to solve. Now let's have a look at some graphs of exponential functions. So this is simply typing, I guess, doing a table of values. So this one's already done for you. 2 to the power of negative 3 means 1 on 2 cubed, and 2 cubed is 8, so that's where this comes from. 2 to the power of negative 2 is 1 on 2 squared, which is 1 on 4. 2 to the power of negative 1 is 1 on 2 to the 1. 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 squared is 4. 2 cubed is 8. Okay, and then subbing into this other exponential equation, 2 to the power of negative x, where x is -3, this becomes 2 to the power of 3, to the power of -3, which is 2 to the power of 3, which is 8. And the next one here, we've got 2 to the power of -2, which is 2 to the power of 2, which is 4. 2 to the power of 1, 2 to the power of 0. Now we've got 2 to the power of -1. So it's almost like a reverse of the first table. 2 to the power of -2 and 2 to the power of -3. Now, if we were to plot these points on a number plane, you would get these curves here. So you can see y equals 2 to the x is increasing as we go from left to right, and y equals 2 to the -x you can see is decreasing as we go from left to right. Now, in this purple curve here, where we've got y to the power of 2x plus 1, just like when we had parabolas and we plussed 1, they shifted up by 1. Same with exponential functions. We're just shifting that whole graph up by 1. And you can see the asymptote here is y equals 1 for the purple graph, and asymptote for both y equals 2 to the x and y equals 2 to the -x is y equals 0. Okay, using your calculator now, I want you to find the e button so that we can find the value of e cubed. And it is right here in yellow, which means you're going to type in e cubed in your calculator, you're going to have to press shift and then that button. And then you can see the e already comes up on your screen. So you just need to type in 3 and then maybe rounding that number to one decimal place, we'll get 20.09. Okay, number 2, very similar. So we're going to press the fraction button first on our calculator and then a 1, arrow down to the denominator, press the shift and then this new button to get the e already typed in your calculator, and then you enter a 2 to make it 1 on e squared, press equals, and to one decimal point that is going to be 0, maybe we'll do it to 2 decimal places, 0.14. Okay, differentiating exponential functions. Now, e is a unique number where the derivative of e to the x equals e to the x. And in class, I'm going to show you a demonstration of graphing both of those, graphing the function e to the x and then also graphing the derivative function to show you that they're both equal. Now, so the rule to differentiating these, when we've just got a constant in the front here, the derivative of 5e to the x is just going to be 5 times the derivative of e to the x, which is e to the x. When you are differentiating in example 2, the subtracted sum or the difference of two different functions, you differentiate them separately as you would a polynomial. So the derivative of e to the x is e to the x, and the derivative of minus x squared is going to be minus 2x. In example number 3, notice how there's an x there and an x here. We've got two functions which have been multiplied, which means we are going to need to use the product rule, where u is negative 8x squared, u dash is negative 16x, v is e to the x, and v dash is also going to be e to the x. So that means the derivative will be insides, so negative 16x e to the x plus outsides, and outsides I'll go back to in blue is those, multiplying those two together, and it'll be minus 8x squared e to the x. Okay. You don't need to factorise or anything. Maybe later if you wanted to find stationary points, that would definitely help, because remember, the stationary points are found by making the first derivative equal to 0, so it will definitely help to find those points by factorising. But if you're just differentiating, that answer that we've got there is perfectly fine. Number 4, we have a function divided by another function, which means we need to use the quotient rule to differentiate this. So our u is the numerator, which is 2e to the x, which means our u dash is also 2e to the x. Our denominator v is x cubed plus x, and our v dash then is 3x squared plus 1. So our quotient rule is insides 2e to the x times x cubed plus x minus the outsides. I don't really have room for this. I might see if I can squeeze it in. So minus 2e to the x outside of 3x squared plus 1 all over v squared. So x cubed plus x squared. So just expanding and collecting like terms on the numerator, we will get 2x cubed e to the x plus 2x e to the x minus 3 times 2 is 6 x squared e to the x, and then minus 2 e to the x all over the denominator squared. And let's just see if we have any like terms. X cubed e to the x, nope. X e to the x, nope. X squared e to the x, nope. No like terms, so we can leave our answer like that. We can't simplify that any further. One last example. Find the equation of the tangent to the curve y equals e to the x at the point where x equals 1. The equation of the tangent. Remember, a tangent is a straight line, so we need to know the gradient of that straight line and a point on that straight line. Then we can use the point gradient formula. So let's find the gradient. First we'll find the gradient function. If y equals e to the x, then y dash also equals e to the x. Let's find the gradient at this point, x equals 1. At x equals 1, y dash is going to equal e to the 1, which is just e. So that's the gradient of our tangent. Now we have our gradient. We've got our x-coordinate of our point. We need to find the y-coordinate of our point. Here we've got the equation for our function, y equals. So we can just sub x equals 1 in here, and we'll get our y-coordinate. You can see y equals e to the 1, which is also just e. So our point is going to be 1e. And so there's our point, there's our gradient. Let's now use the point gradient formula. So y minus e equals e outside of x minus 1. And you get ex minus e. And let's put this in general form. So general form, the x term goes first, and the y term plus the e over. That's it. So there's the equation of the tangent to the curve y equals e to the x at the point where x equals 1.